Okay, let me ask you something. Have you ever been in a situation where someone asks you, hey, how would you design a pipeline that handles 10 million events a day? And you just go blank. And you know the tools. You have used Kafka, you have written Spark jobs, but you don't really know where to start answering that? That's exactly what this course is about. Not teaching you what Kafka is, because I think you probably already know that. It's about teaching you how to think when someone puts a blank whiteboard in front of you and says, go. So over the next 90 minutes, that's what we are doing. We are going to build a complete data system from scratch. Every layer, every decision, every trade-off, using one running example the entire way through. And by the end of this, you will have a mental model that you can apply to any data engineering problem, whether that's in an interview, a design problem, or actual production work that you're doing at your job. So let's get started. Look, whatever I'm showing you in this video, it's just the overview. This is the 30,000 foot view. But if you actually want to crack a product-based company like Google, Meta, Netflix, Amazon, obviously you need to go way deeper than this. You need to know how to design systems end-to-end, how to handle follow-up questions, and how to think about trade-offs on the spot. That's exactly what I have built here. It's a complete system design resource. Real interview questions, detailed walkthrough, architecture patterns, the stuff that actually comes up in interviews. Everything in this video is chapter 1. The product is the full book. The link is in the description. If you are serious about landing that offer, go check it out. Alright, back to it. Now, here's something nobody really talks about. Data engineering system design is fundamentally different from regular software engineering system design. If you come from a software background, you're used to thinking about things like, how do I handle a million users hitting my API? How do I make sure this service doesn't go down? How do I keep response times under 200 milliseconds? That's valid. But as a data engineer, your problems are different. You're not just worried about the system staying up. You're worried about, is the data correct? Is it late? Is it complete? Did something upstream change? And now everything downstream is broken and nobody noticed for 3 days. And that last part is the killer, the silent failure. In software engineering, if your API goes down, users scream immediately. You know about it in seconds, but in data engineering, a pipeline can produce subtly wrong numbers for weeks before anyone catches it. An analyst builds a dashboard on bad data. A data scientist trains a model on corrupted features. Decisions get made. And by the time someone says, hey, these numbers don't look right, the damage is already done. The users of your system aren't end users clicking buttons. They're analysts, data scientists, machine learning models, business executives making million-dollar decisions based on what your pipeline produces. And if your pipeline gives them bad data, they make bad decisions. That's a different kind of failure. That's why correctness and observability matter so much more in our world than raw uptime. So before we get into tools and architecture, I want to give you three concepts that are going to come up constantly, and I mean constantly. Every module, every design decision, every interview question loops back to one of these three. First one, scalability. Pretty simple idea, right? Your system should handle more data without you having to completely rebuild it. But the thing people miss is there are two kinds of scale, and they work very differently. You scale up, sometimes called vertical scaling, by making one machine bigger. More CPU, more RAM, bigger disk. That works up to a point, but there's a ceiling. You can only make one machine so powerful. And if that machine goes down, everything goes down. You scale out horizontal scaling by adding more machines. Instead of one massive server, you spread the work across 10 or 100 or 1,000 smaller ones. That's why things like Spark and Kafka are built the way they are. They're designed from the ground up to spread work across a cluster. You add capacity by adding nodes, not by buying a bigger box. Data systems almost always want to scale out, and the reason is simple. Data grows faster than hardware gets better. Your company's data volume might double every year. Moore's law isn't keeping up with that. So you need systems that grow by adding machines, not by replacing them with bigger ones. Second, reliability. Your pipeline is going to fail. I promise you, it is going to fail. A source system changes its schema without telling you. A network blips at 3 a.m. Someone drops a table, an API starts rate limiting you. A Spark executor runs out of memory because one partition is 10 times bigger than the others. The question isn't whether failure happens, it's how your system responds when it does. Reliable systems fail gracefully. They retry with backoff. They alert the right people. They have circuit breakers so one failing component doesn't cascade and take everything down. And most importantly, they don't silently produce wrong numbers that end up in a board presentation. A good mental model is this: design for the bad day, not the good day. On a good day, everything works. Any architecture looks fine on a good day. The difference shows up when your source database is slow, your Kafka cluster has a broker down, and your Spark job is competing for resources with 3 other teams. That's when your design choices matter. Third, and this one trips people up: latency versus throughput. These are not the same thing, and optimizing for one often directly hurts the other. Latency is how fast one piece of data moves through your system. From the moment an event happens, a customer clicks buy, to the moment that event is queryable in your warehouse or available to your machine learning model. That's latency. Throughput is how much data you can move in total over a given time period. How many events per second can your pipeline handle before it falls behind? Here's the tension. If you want really low latency, you process data the moment it arrives, one event at a time. No waiting, no batching, but that means you're paying the overhead of processing, the network call, the write, the commit for every single event. That overhead per event is high. Your throughput suffers. If you want high throughput, you batch things up and process them together. You amortize the overhead across thousands or millions of events, way more efficient. But now each individual event has to wait for the batch to fill up before it gets processed. Your latency goes up. That trade-off is literally behind every batch versus streaming conversation you'll ever have. When someone asks you, should we use batch or streaming? What they're really asking is, where do we sit on the latency throughput curve for this specific use case? Okay, cap theorem. This comes up in interviews a lot, and people either over-explain it or completely avoid it. Let me just make it simple. CAP stands for consistency, availability, and partition tolerance. The theory says you can only reliably guarantee 2 of the 3 in a distributed system. Now here's what that actually means in practice. Partition tolerance, meaning your system keeps working even if some nodes can't talk to each other. That's basically not optional. Networks fail, switches go down, data centers have outages, so you're always choosing P, which means the real choice is between C and A. Consistency means every time you read data, you get the most recent version, no stale reads. If you just wrote something, you'll see it immediately on the next read, no matter which node you hit. Availability means the system always responds to requests, even if it might give you slightly old data. It never says, sorry, I can't answer right now because I'm not sure I have the latest version. So think about it this way. Your e-commerce order database, you really want consistency there. If someone places an order and then checks their order history, it better show up. You can't have 2 nodes disagreeing about whether an order exists. If the payment went through but the order doesn't appear, that's a support ticket, that's a refund, that's a customer you might lose, that's PostgreSQL territory, that's CP. But your product recommendation system, if it shows you a slightly stale list of recommended items for half a second, nobody cares. Nobody even notices. You want it to always respond fast, even if the recommendations are a few seconds behind. That's Cassandra territory. That's AP. And here's where this gets really practical for data engineering specifically. Think about your data warehouse. When an analyst runs a query, do they need real-time consistency with the source database? Almost never. They're analyzing trends, running aggregations, building reports. A few minutes of stillness is completely fine. That's why most analytical systems lean AP. They prioritize availability and speed over strict consistency. But your data quality checks, those need consistency. If you're validating that row counts match between source and destination and you're reading stale data, You'll either miss real problems or fire false alarms. Context matters. The question to ask in an interview is, what's the cost of stale data in this specific context? Answer that, and you know which way to go. Alright, so here's the full picture of what we're going to build across this course. Every data system has basically the same skeleton. You've got your sources, databases, APIs, event streams, files, whatever. Data comes in through an ingestion layer, that's Kafka, Fivetran, custom connectors, things like that. It lands somewhere in storage, S3, Snowflake, Delta Lake, then you process and transform it. Spark, dbt, Flink, you orchestrate all of that with something like Airflow. So it actually runs on a schedule and you know when it breaks, and then it gets served to a dashboard, to a data scientist's notebook, to an ML model's feature store. That's the skeleton. Every module in this course is one layer of that skeleton, and we're going to go deep on each one. Not just what the tools are, but why you'd pick one over another, what breaks in production, and how to reason about the trade-offs like a senior engineer. And we're going to use the same example throughout. An e-commerce platform, millions of users, hundreds of thousands of transactions a day, multiple teams that all need data in different ways. Your analytics team wants clean aggregated tables, your ML team wants raw features, your product team wants real-time metrics. Every decision we make, we're making it for that system. So by the end, you don't just have theory, you have a complete design you actually understand. Okay, let's start at the beginning. How does data actually get into your system in the first place? That's module 1, ingestion. Let's go. So the first question in any data system is, how does data actually get in? Sounds simple, but the decisions you make here affect everything downstream. The wrong ingestion pattern, and you're either drowning in latency, burning money on compute, or losing data you didn't even know you were losing. There are two fundamental ways to move data, batch and streaming. Batch is exactly what it sounds like. You collect data over a period of time and process it all at once. Think of it like doing laundry. You don't wash one sock the moment it gets dirty. You wait until you have a full load, then you run the machine. Most traditional data pipelines work this way. Every hour, every night, you pull everything that happened since the last run and load it in. Simple, predictable, easy to reason about, easy to debug when something goes wrong. And here's what people underestimate about batch. It's really good at being efficient. When you process data in bulk, you can compress it better, you can optimize your queries better, you can use resources more efficiently. There's a reason the vast majority of data pipelines in production today are still batch. It works. Streaming is the other extreme. Data gets processed the moment it arrives. Every event, every click, every transaction as it happens. Think of it less like laundry and more like a live news feed. Things appear as they occur. Now here's the question people always ask. Which one should I use? And the honest answer is, it depends on how much the age of your data matters. Ask yourself, what's the business cost of data being 1 hour old versus 1 second old? If your business analysts need yesterday's sales numbers every morning, batch is completely fine. A daily or hourly refresh gives them exactly what they need. If your fraud detection system needs to flag a suspicious transaction before it completes, you need streaming. You literally cannot wait an hour. By then the money is gone. If your recommendation engine updates product suggestions, does it need to react within milliseconds of a click? Or is refreshing every 15 minutes good enough? For most e-commerce sites, 15 minutes is fine. For a live trading platform, absolutely not. The thing is, streaming is harder to build, harder to maintain, harder to debug, and more expensive to run. Failure modes are more complex. State management is tricky exactly once processing is genuinely difficult. So the rule of thumb is use batch unless your use case genuinely requires real time. Don't add streaming complexity just because it sounds impressive on a resume. I've seen teams spend months building a real-time pipeline only to find out their stakeholders check the dashboard once a day in the morning. That's a batch problem dressed up as a streaming problem. Don't fall into that trap. Within those two models, there's another decision. Does your source system push data to you, or do you pull it from the source? Push means the source system sends data to you when something happens. An event fires, your system receives it. This is how webhooks work, how Kafka producers work. The source is in control of timing. Pull means you go and fetch the data on your schedule. You query the database every hour. You call the API every 5 minutes. You are in control of timing. Neither is better by default. Push gives you lower latency. You get data faster because you're not waiting for your next scheduled pull. But it means the source system needs to know about you, needs to be configured to send events to your endpoint, and you need to be able to handle whatever volume it throws at you. Pull is simpler to set up in a lot of cases. You just write a query, but you're always slightly behind. And if you pull too often, you risk hammering the source system. Pull too infrequently and your data gets stale. Finding that balance takes tuning. In practice, most batch pipelines are pull-based, most streaming pipelines are push-based, but there are plenty of exceptions. Now there's a third pattern that's worth understanding, and it sits somewhere between push and pull. It's called change data capture, or CDC. The idea is instead of querying the source database directly, you read its transaction log. Every insert, update, and delete that happens in that database gets recorded in a log, and CDC tools tap into that log to capture changes as they happen. Why is this powerful? Because you're not putting any extra load on the source database. You're not running expensive select queries against it. You're just reading a log that already exists, and you get every change, not just a snapshot of the current state. Tools like Debezium do this for databases like Postgres, MySQL, and MongoDB. They read the WAL, the write-ahead log, and stream changes into Kafka topics in near real time. From there, your downstream consumers can pick up those changes however they want. For our e-commerce platform, CDC is incredibly valuable. Your orders database in Postgres is a critical transactional system. You do not want your analytical pipelines running heavy queries against it during peak hours. With CDC, you capture every order, every status update, every cancellation from the log without touching the production workload at all. The catch is CDC can be complex to set up initially. You need to configure the database to expose its logs. You need to handle schema changes carefully because if a column gets added or renamed in the source, your CDC stream needs to adapt. And you need to think about initial loads. The very first time you set up CDC, you need a full snapshot of the table before you can start consuming incremental changes. But once it's running, it's one of the cleanest ways to keep your analytical systems in sync with your transactional systems. Okay, let's talk about Kafka because it comes up in basically every data engineering interview, and it's worth really understanding what it's doing under the hood. Kafka is a distributed event streaming platform. At its core, it's a system where producers write messages and consumers read them. But what makes it powerful is the design decisions behind it. Data in Kafka is organized into topics. Think of a topic like a category. You might have an orders topic, a clicks topic, a payments topic. Each topic is split into partitions, and this is where the scalability comes from. Different consumers can read from different partitions in parallel. Let me make that concrete. Say your orders topic has 12 partitions. You can have 12 consumers, each one reading from a different partition, processing messages simultaneously. You've just parallelized your ingestion by 12 times. Need more throughput? Add more partitions and more consumers. That's horizontal scaling in action. Here's the thing that confuses people at first. When a consumer reads a message from Kafka, the message doesn't disappear. It stays there. This is fundamentally different from traditional message queues like RabbitMQ, where once a message is consumed, it's gone. Kafka keeps messages for a configurable retention period, days, weeks, even indefinitely if you want. And each consumer group tracks its own position, called an offset, independently. What that means practically is you can have your data warehouse loading from the orders topic and your fraud detection system reading from the exact same orders topic, and your recommendation engine also reading from it completely independently at their own pace. They don't interfere with each other at all. The warehouse consumer might be an hour behind, processing in batches. The fraud system might be consuming in real time, milliseconds behind the producer. Both are fine, both work, and if something goes wrong, your warehouse job fails overnight, it just picks up from where it left off. The data is still there waiting. You don't lose anything. You don't need to ask the source system to resend. That replay capability is one of the most valuable things about Kafka. It's not just a pipe, it's a buffer with memory. And that memory is what makes so many downstream patterns possible. Now, let's talk about how messages get distributed across partitions, because this matters more than people think. When a producer sends a message to Kafka, it can either let Kafka distribute it randomly across partitions, round robin style, or it can specify a partition key. If you key your order events by customer ID, then all events for the same customer always go to the same partition. That guarantees ordering per customer. Why does ordering matter? Because if you have an order placed event and then an order cancelled event for the same order, and they end up on different partitions, different consumers might process them out of order. You could process the cancellation before the placement. That's a problem. The rule is, if ordering matters for a given entity, use that entity's ID as your partition key. All events for that entity will be in the same partition, and within a partition, Kafka guarantees ordering. But be careful, this is also where data skew can creep in. If one customer generates massively more events than others, that partition gets hot. We'll talk more about skew when we get to processing in Module 3. For batch ingestion, Fivetran and Airbyte are the two main players right now. They handle connectors to hundreds of sources, databases, SaaS tools like Salesforce and HubSpot, APIs, file systems. You configure the connection, set a sync schedule, and they handle the rest. Fivetran is fully managed. You don't run any infrastructure. It just works. The trade-off is cost. It charges based on monthly active rows, and at high volumes that adds up fast. Airbyte is open source. You can self-host it and avoid per row pricing. But now you're responsible for running and maintaining the infrastructure. Connectors can be less polished than Fivetrans. It's a classic build versus buy trade-off. For streaming, Kafka is the open source standard. If you're on AWS and don't want to manage Kafka yourself, Amazon Kinesis does a similar job with less operational overhead. But Kinesis has some limitations: shorter retention, less flexibility with consumer groups, and you're locked into the AWS ecosystem. Confluent Cloud gives you managed Kafka if you want the Kafka API without the ops burden. Now, 3 pitfalls that will catch you if you're not thinking about them. First, back pressure. This is what happens when your producer is writing data faster than your consumer can process it. Messages pile up, lag grows, and eventually you either drop data or your system falls over. The fix is monitoring consumer lag actively and scaling your consumers when it starts growing. In Kafka, consumer lag is the difference between the latest offset and the consumer's current offset. If that number is growing, you're falling behind. Add more consumers, add more partitions, spread the load. Most production Kafka setups have alerts that fire when consumer lag exceeds a threshold, say more than 5 minutes behind. Second, late arriving data. In streaming systems especially, events don't always arrive in the order they happened. A mobile app might batch events locally when there's no signal and send them all at once when connectivity returns. So you get an event timestamped 3 hours ago, arriving right now. This is a bigger deal than it sounds because most analytics depend on time windows. If you're calculating hourly revenue and a purchase event arrives 2 hours late, does it count in the hour it happened or the hour it arrived? You have 3 options. You use a watermark, you wait a defined period for late events before closing a time window. So you say, I'll keep the window open for an extra 30 minutes past its end time. Any event arriving within that grace period still gets counted correctly. You reprocess. You keep raw data and periodically rerun calculations to catch stragglers. This is the lambda approach. Your real-time layer gives you approximate numbers quickly, and your batch layer corrects them later. Or you drop late events, acceptable if they're rare and the cost of missing them is low. If 0.1% of your clickstream events arrive late, you might just accept the tiny inaccuracy. Third pitfall, schema evolution. Your source systems will change. A new column gets added, a field gets renamed, a data type changes from string to integer. If your ingestion pipeline assumes a fixed schema, it breaks. The fix is using schema registries, like the Confluent schema registry for Kafka, which tracks schema versions and enforce compatibility rules. You can require that schema changes are backward compatible, meaning old consumers can still read new data. This saves you from the 3 a.m. page where your pipeline crashed because someone added a field to the orders table. So that's ingestion. You now have a mental model for how data enters the system, the trade-offs between batch and streaming, push and pull, how Kafka is built and why, and the pitfalls that catch people in production. Next up, once data arrives, where does it actually live? That's the storage layer. And there are more options than you might think. Module 2. Alright, so data is flowing in, now what? Where you store it and how you store it has a bigger impact on your system's performance and cost than almost any other decision you'll make. And there are genuinely different options here, not just different tools, but different philosophies. So let's break it down. 3 terms you'll hear constantly: data lake, data warehouse, data lakehouse. People use them interchangeably sometimes, and they absolutely should not. A data lake is essentially cheap object storage. Think S3 or Google Cloud Storage, where you dump raw data in whatever format it came in: JSON, CSV, Parquet, Avro, images, log files, doesn't matter. You store it all, you figure out the structure later. The upside is it's incredibly cheap and incredibly flexible. S3 costs a couple cents per gigabyte per month. You can store petabytes without breaking a sweat, and there's no schema enforcement. So if your source data is messy or changing frequently, the lake doesn't care. It takes everything. The downside is that without discipline, it becomes a data swamp. Nobody knows what's in there, nothing is documented, files are scattered across thousands of prefixes with inconsistent naming, and querying it directly, just running ad hoc SQL, is slow and painful because the data isn't optimized for analytics. A data warehouse is the opposite philosophy. Snowflake, BigQuery, Redshift, these are optimized specifically for analytical queries. Data goes in clean, structured, with a defined schema. Queries are fast because the system knows the data layout and can optimize accordingly. Warehouses also give you governance features, access controls, audit logs, column level security. When your compliance team asks who accessed customer PII data last month, a warehouse can answer that. A raw data lake usually can't. But warehouses are more expensive, sometimes significantly, and you've got to transform your data before it lands there. You can't just throw raw events in and expect good results. The warehouse expects clean tables with defined types. The lakehouse is the newer idea, and honestly, it's where most modern stacks are heading. The concept is, what if we kept data in cheap object storage like S3, but added a metadata layer on top that gives us warehouse-like features: ACID transactions, so writes are atomic and consistent; schema enforcement, so you catch bad data before it lands; time travel, so you can query what the data looked like yesterday or last week or last month. That's what Delta Lake and Apache Iceberg do. They're not storage systems themselves. They're table formats that sit on top of object storage and add structure. You get the cost of a lake with the reliability of a warehouse. Iceberg in particular has been gaining massive momentum. It's what Netflix, Apple, and LinkedIn use internally. It supports schema evolution natively, meaning you can add columns, rename fields, change types without breaking existing queries. And it has excellent partition evolution. You can change your partitioning strategy without rewriting all your data. For our e-commerce platform, raw event data, click streams, application logs, CDC streams that lives in the lake or lakehouse layer on S3, cleaned, aggregated, business-ready data that lives in Snowflake for the analytics team. Both have a role. The lake is your archive, your source of truth, your reprocessing safety net. The warehouse is your fast query engine for business users. Now let's talk about how data is physically stored, because this is one of those things that really clicks once you see it. Traditional databases, Postgres, MySQL, store data row by row. Every field for a customer, their ID, name, email, address, phone number, order count, sign up date, all stored together on disk one after another. When you look up one customer, that's great. You read one row, you get everything. But think about what an analyst actually does. They don't say, give me everything about customer 123. They say, give me the total revenue across all orders last month. To answer that, a row-based system has to read every single row, every order, every field, even the fields it doesn't need. Customer names, shipping addresses, product descriptions, just to get to the revenue column. If you have a billion orders with 20 columns each, but you only need 2 columns for your query, you're reading 10 times more data than necessary. That's wasted I/O. That's wasted money on cloud storage reads. That's a slow query. Columnar storage flips this. Instead of storing each row together, it stores each column together. All the revenue values packed in one place. All the timestamps packed in another. All the customer IDs together. Now, when your analyst runs that aggregation query, the database only reads the 2 columns it actually needs. It skips everything else entirely. On that billion row table, instead of reading all 20 columns, you read 2. That's a 90% reduction in data scanned. And it gets even better, because when similar values are stored together, compression is much more effective. A column of timestamps has way more repeating patterns than a mixed row of strings, numbers, and dates. Compression ratios of 5 to 1 or even 10 to 1 are common with columnar formats, which means less storage cost and faster reads because there's less data to move off disk. This is why Parquet is the go-to file format for analytical workloads. It's columnar, it's compressed, and it includes metadata, like min and max values per column chunk, that lets query engines skip entire file sections without reading them. That's called predicate pushdown. The engine pushes your where clause down to the storage layer and only reads the chunks that could possibly match. Parquet versus ORC is a question you'll sometimes hear. Both are columnar. ORC was developed by the Hive community and has better built-in indexing. Parquet came from Cloudera and Twitter and has broader ecosystem support. It's the default in Spark, in Iceberg, in most modern tools. For almost all cases, just use Parquet. You won't go wrong. Avro is the other format worth knowing, but it's raw-based. It's great for data serialization, for Kafka message formats, for storing individual records. But for analytical queries, columnar beats it every time. Rule of thumb, if your use case is transactional, lots of individual record lookups, inserts, and updates, row-based. If it's analytical, lots of aggregations across huge datasets, columnar, and for most data engineering work, analytical is what you're building for. Okay, partitioning. This is one of the highest leverage things you can do for query performance, and I want to make sure it really lands. Imagine your orders table has 5 years of data, billions of rows. Someone runs a query, show me all orders from last week. Without partitioning, the system scans every single row in that table, all 5 years, billions of rows, to find 7 days worth of data. Partitioning means you physically organize your data into folders based on a column value, usually date. So all orders from March 1st, 2024 live in one folder. All orders from March 2nd in another. When that query comes in asking for last week, the system looks at the folder structure and says, I only need these 7 folders. It skips everything else completely. That's called partition pruning. The difference can be enormous. We are talking going from scanning 500 gigabytes to scanning 1.4 gigabytes for the same query. On a big enough dataset, That's the difference between a query finishing in 3 seconds and one that times out after 10 minutes. That's the difference between a dashboard that loads instantly and one that your analysts stop using because it's too slow. Now there's a trap here, the small files problem. If you partition too granularly, say by hour or by individual user ID, you end up with thousands of tiny files instead of a smaller number of reasonably sized ones, and reading lots of tiny files has its own overhead. Each file requires a separate metadata lookup, a separate read operation, a separate open and close cycle. The overhead adds up. The sweet spot is roughly 100 megabytes to 1 gigabyte per file, partitioned by date for most time series data. If your daily volume is huge, partition by date and a second column like region or category. But don't go finer than you need to. And if you do end up with small files, compaction is your friend. Tools like Iceberg and Delta Lake have built-in compaction. They periodically merge small files into larger ones. Spark can do it too. You just read the partition, coalesce the data, and write it back out. Schedule it as a maintenance job. Your future self will thank you. So how do you actually choose between all these storage options in practice? Start with the question, who are my primary consumers and what are they doing with the data? If it's mostly SQL analysts running reports and dashboards, a warehouse or lakehouse is your answer. The query performance is there. The SQL interface is familiar. The governance and access controls are built in. If you also have data scientists or ML engineers who need raw data, unstructured data, or who want to run Python or PySpark notebooks directly on the data, you need a lake component too. They don't want pre-aggregated data. They want the raw events, the raw features, the full history. They want to experiment. If you need both, and most mature data platforms do, that's where the Lakehouse architecture shines. One storage layer, S3 with Iceberg or Delta on top, multiple ways to access it. Analysts query through Snowflake or Trino, data scientists access through Spark or Pandas. Everyone shares the same underlying data. And then there's cost. If you're early stage, data volumes are modest, and you just need something that works, a cloud warehouse like BigQuery or Snowflake is honestly the right call. Don't over-engineer it. You can always add a lake layer later when you outgrow the warehouse. The lakehouse complexity pays off at scale. At a startup with 100 gigabytes of data, it's unnecessary overhead. One more thing on cost, compute and storage separation. This is one of the most important architectural shifts in modern data platforms. Traditional systems like on-prem Hadoop tied compute and storage together. You scaled them as one unit. Modern systems, Snowflake, BigQuery, Spark on S3, separate them completely. Your data lives in cheap object storage. You spin up compute only when you need it. When the query finishes, compute goes away. You're not paying for idle clusters sitting there doing nothing at 3 a.m. So now you know where data lives and how it's physically organized, but getting it there in the right shape, clean, transformed, ready to use, that's its own problem entirely. That's what Module 3 is about, processing data at scale, how you take raw, messy, high volume data and turn it into something your business can actually use. Let's get into it. Alright, so data is coming in, it's sitting in storage, but raw data is almost never useful on its own. It's got duplicates, it's got nulls. The schema changed 3 weeks ago and nobody told you. Timestamps are in 5 different formats. Customer IDs don't match across systems. Revenue is stored as a string in one table and a float in another. You need to join it with 3 other tables before it means anything. Processing is where you take that raw mess and turn it into something people can actually use. And when you're doing that at scale, billions of rows, terabytes of data, the decisions you make here really matter. Apache Spark is the dominant tool for large-scale batch processing. If you're working with data at any serious volume, you're going to encounter it. Even if you're using dbt and Snowflake for most of your work, understanding Spark helps you reason about distributed processing in general. Here's the mental model. When you write a Spark job, say read this dataset, filter these rows, join with another table, aggregate by customer, Spark doesn't just execute that line by line. It builds a DAG first, a directed acyclic graph, basically a plan of all the operations and how they connect. Then it optimizes that plan before running anything. The Catalyst optimizer figures out the most efficient order of operations. Can I push this filter down before the join so I'm working with less data? Can I skip reading columns I don't need? Can I combine these two transformations into one pass? Only then does it actually touch the data. This lazy evaluation, where nothing happens until you trigger an action like a write or a collect, is one of Spark's most important features. It means Spark sees your entire pipeline before executing any of it and can make global optimizations that would be impossible if it executed step by step. Most operations in Spark are what we call narrow transformations, filtering rows, selecting columns, adding calculated fields. These happen within a single partition on a single machine. No data movement needed. They're fast and cheap. But then there's the shuffle, and the shuffle is expensive. A shuffle happens when Spark needs to redistribute data across machines. Joins are the classic example. If you're joining orders with customers on customer ID, Spark needs to make sure all orders for customer 123 are on the same machine as the customer 123 record. To do that, it writes data to disk, sends it over the network to other executors, reads it back. That's disk I/O plus network I/O. That's slow. That's the bottleneck. Group by operations also trigger shuffles. If you're aggregating revenue by product category, all records for the same category need to be on the same machine. Same mechanism, same cost. The number one rule for writing fast Spark jobs: minimize shuffles, filter early, reduce data volume before joins, use broadcast joins when one table is small. Every shuffle you avoid is minutes or hours saved on large datasets. Now, if you're working in a warehouse environment like Snowflake or BigQuery, dbt is doing essentially the same thing conceptually. It's building a DAG of SQL transformations, staging models that clean raw data, intermediate models that join and enrich, MART models that serve business users. Same concept, different execution engine. The warehouse handles the distributed processing under the hood. You just write SQL and dbt manages the dependency graph. Spark is great for batch, but what about when you genuinely need to process data in real time? That's where Apache Flink comes in. The key difference, and this is worth understanding, is that Spark streaming isn't actually real time. It's micro batch. It collects a small window of events, say every 2 to 10 seconds, and processes them as a mini batch. It's faster than traditional batch, but there's still an inherent delay. Your latency floor is the micro batch interval. Flink processes events truly one at a time. As they arrive, we're talking millisecond latency. An event hits Kafka, Flink picks it up, processes it, and writes the result, all within milliseconds. And it does this while maintaining state, meaning it can remember things across events. How many orders has this customer placed in the last hour? What's the running average transaction amount for this merchant? Is this sequence of events, login from new device, immediate high value purchase, different shipping address, part of a fraud pattern? That kind of stateful processing, where you need to track patterns and accumulate information across a stream of events, is where Flink really shines. Spark streaming can do stateful processing too, but the micro batch model makes it clunkier. Flink also handles time properly, which sounds simple but is actually one of the hardest problems in stream processing. It distinguishes between event time, when something actually happened in the real world, and processing time, when your system received and processed it. For accurate analytics, that distinction matters a lot. If you're calculating hourly revenue and an order event arrives 5 minutes late, you want it counted in the correct hour, the hour the customer actually placed the order, not the hour your system happened to receive it. Flink's watermark mechanism handles this. It tracks how far behind reality your stream might be and holds windows open accordingly. If your use case is fraud detection, real-time personalization, live dashboards that update by the second. Flink is the tool. If you can tolerate a few minutes of delay, Spark Streaming is simpler to operate and has a much larger talent pool. Okay, so this leads into one of the bigger architectural decisions in streaming systems, Lambda versus Kappa. Lambda architecture came first. The idea was you have two separate pipelines running in parallel, a batch layer that processes all historical data accurately but slowly, and a speed layer that processes incoming data in real time but might be slightly approximate. You merge the results from both to serve queries. Sounds reasonable in theory. In practice, it's a nightmare. You're maintaining two completely separate code bases doing essentially the same thing. Your batch logic is written in Spark. Your streaming logic is written in Flink or Spark Streaming. They use different API, different testing frameworks, different deployment processes, and they drift apart over time. A bug gets fixed in one but not the other. A business rule changes, say how you calculate discounts, and someone updates the batch pipeline but forgets the streaming one. You end up with your real-time numbers and your historical numbers disagreeing, and nobody knows which one is right. Your stakeholders see two different revenue numbers and lose trust in both. Kappa architecture is the response to that. The idea is, what if we just had one pipeline, streaming only, and when you need to reprocess historical data, you just replay it through the same pipeline. This is where Kafka's message retention becomes crucial, because if your raw events are still sitting in Kafka or backed up in object storage, you can replay from the beginning, run it through your streaming pipeline, and rebuild your entire history. One code base, one set of logic, one version of the truth, no divergence. The industry has largely moved toward Kappa. Tools like Flink combined with Iceberg for storage make it genuinely practical now. Lambda still exists in legacy systems, but if you're designing something new, Kappa is almost always the cleaner choice. One more critical topic, because it will absolutely bite you in production if you're not aware of it, data skew. Here's the scenario. You're running a Spark job, joining your orders table with your customers table. You've got your cluster, say 10 workers, and you expect the work to be spread evenly across all of them. Each worker handles roughly the same amount of data. They all finish around the same time. Job done in 4 minutes. But what if one of your customers is Amazon or Walmart? They have 10 million orders. Every single one of those orders, when you join on customer ID, gets routed to the same partition, the Amazon partition. One worker gets absolutely hammered, while the other 9 sit there basically idle. Your job takes 40 minutes instead of 4, and it's because of one key. That's data skew, and it's surprisingly common. It shows up in joins where one key has disproportionately more records. It shows up in aggregations where one group is massive. It shows up in windowed operations where one time window has a spike. The way you spot it is by looking at task execution times. Open up the Spark UI. Go to the stage that's taking forever. If you see 99 tasks that finished in 10 seconds and one task that's been running for 20 minutes, that's skew. That one task has a hot partition. The fixes depend on the situation. Salting is the classic technique. You artificially add a random suffix to your hotkeys. So customer ID Amazon becomes Amazon underscore 1, Amazon underscore 2, Amazon underscore 3. This spreads the data across multiple partitions. You do your join or aggregation on the salted key, then aggregate the results back together afterwards. Extra step, but it eliminates the bottleneck. Broadcast joins work when one of your tables is small enough to fit in memory. Instead of shuffling the big table, you send a copy of the small table to every worker. Now the join happens locally on each worker. No shuffle at all. If your customer dimension table is 50 megabytes, broadcast it. Don't shuffle your billion row orders table. Adaptive Query Execution, or AQE, is a feature in modern Spark that handles some skew automatically. It monitors partition sizes at runtime, and if it detects a hot partition, it splits it. This doesn't solve every case, but it catches the easy ones without you writing custom code. Make sure it's enabled, it's on by default in Spark 3. A few more optimization tips while we're here. Cache strategically. If you're using the same dataset in multiple branches of your DAG, cache it in memory after the first read. Otherwise, Spark will recompute it from scratch each time, but don't cache everything. Memory is finite and unnecessary caching causes spills to disk. Watch your file sizes on write. When Spark writes output, the number of output files equals the number of partitions. If you have 200 partitions but only 10 megabytes of data, you get 200 tiny files. Use coalesce or repartition before writing to control output file count. And always filter early. The less data that flows through your pipeline, the faster everything runs. Push your where clauses as early as possible. Drop columns you don't need right at the start. The catalyst optimizer helps, but being explicit helps more. So now you can move data in, store it efficiently, and transform it at scale. But here's the thing, all of those processes need to run on a schedule. They need to depend on each other in the right order. And when something breaks, and it will, you need to know about it before your stakeholders do. That's orchestration. That's module 4. Let's go. So you can move data, store it, and process it. But a pipeline that only runs once isn't very useful. In the real world, pipelines run on schedules. They depend on each other. Ingestion has to finish before transformation can start. Transformation has to finish before the dashboard refreshes. They fail. And when they fail, you need to know exactly what broke, why it broke, and how to fix it without making things worse. That's orchestration. And it's one of the most underrated skills in data engineering. Good orchestration is invisible. Everything just runs. Bad orchestration, that's the 3 a.m. page, the stale dashboard, the analyst slacking you asking why the numbers didn't update. Apache Airflow is the most widely used orchestration tool in the industry. The core concept is the DAG, a directed acyclic graph of tasks. Each task in your DAG is a unit of work. Extract from Postgres, run a dbt model, execute a Spark job, load into Snowflake, run a data quality check, send a Slack notification. You define the dependencies between tasks, and Airflow handles scheduling, retries, and monitoring. The power of DAG is that they encode your pipeline's logic in a way that's both executable and understandable. You can look at a DAG and immediately see this task depends on those two tasks. These three tasks can run in parallel. If this one fails, everything downstream stops. A typical daily pipeline for our e-commerce platform might look like this. 3 extract tasks running in parallel, pulling from Postgres, Stripe, and our CRM. Then they all fan into a staging transform task that runs dbt staging models. Then a mart transform task that builds the business layer tables. Then 3 load or publish tasks fan out. One refreshes the Tableau dashboards, one updates the ML feature store, one exports a CSV for the finance team, then a final notification task fires when everything's done. That whole DAG, source to notification, runs every morning at 6 a.m. If any task fails, Airflow retries it. If retries are exhausted, it alerts you and stops downstream tasks from running on incomplete data. Alternatives to Airflow include Prefect and Dagster, both more modern, better developer experience, much better testing story. Dagster in particular has the concept of software-defined assets, where instead of defining tasks, you define the datasets you want to exist, and Dagster figures out how to build them. If you're starting fresh, definitely worth evaluating. But Airflow is still what you'll see in the majority of companies, and it's what interviewers usually expect you to know. Here's a concept that I cannot stress enough: idempotency. An idempotent pipeline is one where running it multiple times produces the same result as running it once. If your pipeline runs at 2 a.m., succeeds, and then someone accidentally reruns it at 9 a.m., the data should look exactly the same. No duplicates, no extra rows, no corruption. This sounds obvious, but it's shockingly easy to get wrong. If your pipeline does insert into orders, select star from staging, and it runs twice, you now have every row duplicated. That's not idempotent. And it's one of the most common bugs in data pipelines. The standard fix is to use delete then insert, or merge statements, or insert overwrite for partition-based systems. You blow away what was there for that time window and replace it completely. So if the pipeline runs 3 times, you still only have one copy of the data. DBT handles this well with its materialization strategies. Table materialization always drops and recreates, so it's inherently idempotent. Incremental models require more care. You need to define a unique key so DBT knows which rows to update versus insert. Get that wrong and you get duplicates. I've seen teams debug phantom row count growth for weeks before finding a missing unique key in an incremental model. The rule of thumb: design every pipeline to be rerunnable from any point in time. If something goes wrong Tuesday night and you need to rerun, you should be able to backfill Tuesday's data without fear. That's the gold standard. Every pipeline, every task, rerunnable by default. Pipelines will fail. The question is how your system responds. The baseline is exponential backoff with retries. First failure, wait 2 minutes, retry. Second failure, wait 4 minutes. Third, 8 minutes. This handles transient errors, network blips, a temporarily overloaded database, a Spark executor that got killed by the cluster manager, without hammering the system with immediate retries that make the problem worse. But retries have a limit. After 3 or 4 attempts, you need to stop and alert. Don't retry forever, that just masks real problems. Set a max retry count, and when it's exhausted, notify the team. Airflow has SLA miss callbacks. If a DAG doesn't complete by a certain time, it fires a notification. This is critical because some failures aren't errors, they're slowness. Your pipeline didn't crash, it's just running 3 times longer than usual because the source database is under heavy load. It'll eventually finish, but your stakeholders needed the data an hour ago. SLA monitoring catches this. You can hook alerts up to Slack, PagerDuty, email, whatever your team uses. The important thing is that the right person gets notified at the right urgency level. A staging model failing at 2 a.m., Slack message. Someone will fix it in the morning. The revenue dashboard failing before the Monday exec meeting, that's a PagerDuty page. The key metric to track is SLA compliance. What percentage of your pipelines complete within their expected window? A healthy data platform should be above 99%. If you are seeing regular SLA misses, something systemic is wrong. Maybe your data volumes have outgrown your compute. Maybe a source system is degrading. Maybe a pipeline was written for 1,000 rows and now it's processing 1,000,000. Track it over time. Plot it on a dashboard. Review it in your team retrospectives. SLA compliance is the single best indicator of pipeline health. Now, there's another layer of failure handling that often gets overlooked: circuit breakers and dead letter queues. A circuit breaker stops your pipeline from repeatedly hitting a failing dependency. If your source API returns errors 3 times in a row, the circuit breaker trips, and your pipeline stops trying for a cooldown period. Instead of burning through retries and filling up error logs, after the cooldown, it tries again. If it succeeds, great, circuit closes. If it fails, back to cooldown. Dead letter queues are for streaming systems when an individual event can't be processed. Maybe it's malformed, maybe it references a customer that doesn't exist yet. Instead of crashing the whole stream, you route that event to a separate queue for investigation. The stream keeps flowing. You debug the bad events later. This is essential for production streaming pipelines. You cannot let one bad event bring down your entire real-time system. One more thing before we move on: data lineage. Lineage is a map of where your data comes from and where it goes. Every table, upstream and downstream. Every dependency, visible and traceable. If something breaks in your raw Postgres extraction, you need to know immediately which downstream staging models, MAR tables, dashboards, ML features and scheduled reports are affected. Without lineage, you're guessing. You're manually searching through SQL files trying to figure out which tables depend on which. With lineage, you look at the graph and say, this source table feeds these three staging models, which feed these two marts, which feed this Tableau dashboard and this ML feature pipeline. That's the blast radius. That's who you notify. That's what you test after the fix. Tools like OpenLineage, dbt's built-in lineage graph, and platforms like Atlan, DataHub, or Marquez can generate and visualize this automatically. dbt is particularly good here because it already knows the dependency graph from your SQL references. The goal is to know the blast radius of any failure before your stakeholders call you. Proactive communication, hey, the orders data is delayed this morning, dashboards will be refreshed by 9, builds so much more trust than reactive firefighting. Alright, your pipelines are running, they're reliable, they recover from failures, and you know exactly what depends on what. Now, what does the actual data look like when it's stored? How should you structure it for the people who need to use it? That's data modeling, module 5. So data is moving, stored, processed, and orchestrated. But how you actually structure that data, how you model it, determines whether the people consuming it can do their jobs effectively. Bad data modeling means slow queries, confused analysts, and business logic scattered across dozens of different SQL files that nobody can maintain. It means every analyst writing their own version of total revenue and getting slightly different numbers. It means join explosions, fan-out traps, and metrics that don't add up. Good data modeling means fast, trustworthy, easy to understand datasets that people actually use. It means one agreed upon definition of revenue, one customer dimension, one source of truth. The foundation of analytical data modeling is the star schema. It's been around since the 90s, Ralph Kimball's dimensional modeling, and it's still the right default for most use cases. The idea is simple. You have a fact table at the center. This contains the measurable events. For our e-commerce platform, the primary fact table is fact orders. Each row is one order, and it contains the numeric values you'd want to aggregate. Order revenue, item quantity, discount amount, shipping cost, plus foreign keys pointing to dimension tables. Dimension tables describe the who, what, when, and where around those facts. Customer dimension, customer name, email, city, sign-up date, lifetime order count. Product dimension, product name, category, subcategory, brand, price tier. Date dimension, date, day of week, month, quarter, fiscal year, is holiday flag. Channel dimension, mobile, desktop, iOS app, Android app. When an analyst wants to know total revenue by product category last quarter, they join the fact table to the product dimension and the date dimension. Two joins, clean, fast, predictable. When they want revenue by channel by month, two joins. Revenue by customer segment by region, two joins. The star shape means every query follows the same pattern. Join fact to the relevant dimensions, filter, aggregate. The key discipline is keeping fact tables lean, only metrics and foreign keys. Descriptive attributes belong in dimensions. If you start putting customer names directly in the orders fact table, you've broken the model. That customer name is now duplicated across every single order for that customer. Storage bloats, updates become painful, customer changes name, and you have to update millions of fact rows. Another key concept, grain. The grain of your fact table is the level of detail each row represents. In fact orders, each row is one order. That's the grain. If you want to also track individual line items, each product within an order, you need a separate fact table, fact order lines, with a finer grain. Getting the grain right up front is critical. Too coarse, you lose detail. Too fine, queries are slow and storage is expensive. For most analytical use cases, model at the most granular level that makes sense, and let users aggregate up from there. It's easy to go from line level to order level with a sum. It's impossible to go the other direction if you only stored the aggregate. Here's a problem that trips people up. What happens when dimension data changes? A customer moves city, a product changes category, an account manager switches clients, a pricing tier gets restructured. The data has changed. But what about your historical records? Did that sale last year belong to the old category or the new one? That's the slowly changing dimension problem, SCD for short, and there are a few ways to handle it. Type 1, just overwrite, update the record, lose the history. Simple. The customer row always reflects current state, but now you can't accurately report on the past. If a customer was in the enterprise segment when they made a big purchase last year, but they've since been downgraded to mid-market, a type 1 dimension would make it look like that purchase came from a mid-market customer. That's misleading. Type 1 is fine for things that genuinely don't matter historically, like fixing a typo in a customer name or updating an email address. Type 2, keep history by adding a new row. When something changes, you add a new row with the updated values and mark the old row as inactive. Each row gets a valid from timestamp, a valid to timestamp, and an is current flag. So when that customer moves from New York to Chicago, the old row gets valid to set to today and is current set to false. A new row appears with city equals Chicago, valid from equals today, valid to equals some far future date, and is current equals true. Your historical orders, which have a foreign key to the customer dimension, still point to the old row, the New York row, so your historical analysis is accurate. New orders get linked to the new Chicago row. History is preserved. Reporting is accurate. Type 2 is the right default for anything analytically meaningful. It's more complex to implement and query. You need to join on the dimension key and also filter by valid from and valid to. But the accuracy is worth it. DBT has a snapshots feature that handles type 2 automatically. You point it at a source table, tell it which columns to track, and it manages the versioning for you. Highly recommend using it. Now, there's a broader structural trade-off I want to cover, the spectrum between normalized and denormalized models. Normalized models, lots of separate tables, minimal duplication, joined at query time. Your customer data lives in one table, orders in another, products in another, line items in another. 5, 6, 7 tables joined together to answer a single business question. Normalized is cleaner to maintain. One source of truth per entity. If a customer's name changes, you update one row in one table. Done. But every time an analyst wants to answer a question, they're writing multi-table joins. That's slow on large datasets, and it's error-prone, wrong join type, missing filter, accidental fan-out where one-to-many joins inflate your row count. Wide tables, sometimes called one big table or OBT, pre-join everything. Your mart.orders table has customer name, customer segment, customer city, product category, product brand, order date, quarter, channel, revenue, all in one row. No joins needed. Queries are fast and simple. Any analyst can write a group by and get answers. The trade-off is storage and maintenance. Wide tables duplicate data. Customer name is stored on every single order row. And when something changes, say a new business rule about how you categorize channels, you need to rebuild the entire table. The rule I use, normalize in your staging layer, denormalize in your mart layer. Keep your raw and intermediate models clean, modular, well-tested, following proper star schema conventions. Then in your final mart layer, give your end users the wide pre-joined tables they need to be productive. Storage is cheap, analyst time is not. If pre-joining saves your analytics team 15 minutes of SQL writing per query and they run 50 queries a day, that's enormous value. So now you have a complete picture from raw data arriving at your ingestion layer, all the way through to clean, well-modeled tables your analysts and ML teams can actually use. The last module is about pulling all of this together because at some point you're going to be in an interview or in a design meeting and someone's going to say, how would you design this system? And you need a framework for answering that confidently. That's Module 6. Everything you've learned in this course, ingestion, storage, processing, orchestration, modeling, it all comes together in one moment, the system design interview. And here's what I see happen to even good engineers in these interviews. They know the tools, they've built real systems, but they freeze when the whiteboard appears because they don't have a structure. They start drawing random boxes. They jump to Kafka before understanding the requirements. They forget to talk about monitoring. They run out of time because they spend too long on one layer. This module is the structure. The framework I use is called Radio. 5 letters, 5 steps. You go through them in order every time and you'll cover everything an interviewer is looking for. R is requirements. Before you draw a single box, ask questions. What's the scale? How many events per day? How many users? How fresh does the data need to be? Real time, hourly, daily? Who are the consumers? Analysts running SQL, ML models needing features, a product team needing an API. What are the reliability expectations? Can we tolerate some data loss or does it need to be exactly once? Are there any compliance requirements? PII information. You want to spend the first 2 or 3 minutes on this. Interviewers are testing whether you ask the right questions as much as whether you know the right answers. An engineer who clarifies requirements before designing, that's a senior signal. An engineer who immediately starts drawing Kafka, that's a junior signal. A is architecture. Draw the high-level skeleton first. Source, ingest, store, transform, serve, 5 boxes, lines between them. Get the overall flow on the whiteboard before filling in any details. This shows you can think at the system level before diving into component level decisions. D is data model. What does this schema look like? What are the key entities? Is this a star schema with fact and dimension tables? A wide denormalized table? A feature store with point-in-time correct features? What's the grain of your main table? How do you handle slowly changing dimensions? I is infrastructure. Now and only now, you name specific tools and justify each choice. Kafka over Kinesis because you need replay capability and multi-consumer independence. Snowflake over BigQuery because the team already has Snowflake expertise and migration cost is high. Spark over Flink because your latency requirements are minutes, not milliseconds, and Spark is simpler to operate. Every choice should have a reason, and that reason should tie back to the requirements you clarified in step 1. That's the thread that holds your design together. O is observability. Always end here. How do you monitor this system? What metrics do you track? Pipeline compliance, data freshness, row count anomalies, schema drift? What alerts fire when something breaks? How do you know data quality is good before your stakeholders see it? This is the part most candidates skip, and it's the part that separates seniors from juniors. Any engineer can draw boxes and arrows. The senior is the one who says, and here's how we know it's all working correctly. Let's make the R in radio more concrete. 3 questions that unlock most design problems. First, what's the expected data volume and how does it grow? Second, what's the acceptable latency from event to query ready data? Third, who consumes this data and what are they doing with it? These 3 questions constrain your design space immediately. High volume plus low latency equals streaming plus Kafka plus Flink. Moderate volume plus daily freshness equals batch plus Fivetran plus DBT. ML consumers needing point-in-time features. That changes your data model completely compared to analysts needing aggregated dashboards. For capacity estimation, you don't need exact numbers, you need orders of magnitude. Interviewers don't want you to calculate precise metrics. They want to see you can reason about scale. Take our e-commerce example. 10 million events per day divided by 86,400 seconds in a day. That's about 116 events per second average, but traffic isn't uniform. Peak is maybe 5x average, so 580 events per second at peak. Each event is maybe 500 bytes of JSON. That's 5 gigabytes per day raw. 150 gigabytes per month, about 1.8 terabytes per year. That tells you S3 is more than sufficient for storage at pennies per gigabyte. Kafka with 6 to 10 partitions handles 580 events per second comfortably. Kafka can handle hundreds of thousands per second per partition. A single Spark cluster can process 5 gigs in minutes. Snowflake's extra small warehouse can query a 1.8 terabyte dataset efficiently if it's partitioned well. You're nowhere near the scale where you'd need exotic sharding strategies or multi-region replication. That matters because it means you can keep the architecture simpler. Don't design for Google scale if you're operating at startup scale. Back of envelope is the skill. Practice it. Let's walk through a complete design for our e-commerce platform. Sources: Postgres for order data and inventory, Stripe webhooks for payment events, our mobile app and website firing clickstream events through an event SDK, a third-party CRM, Salesforce for customer relationship data. Ingestion: Debezium CDC captures changes from Postgres into Kafka near real-time, no load on the production database. Stripe webhooks flow directly into a Kafka topic. Clickstream events from the app publish to another Kafka topic. Fivetran syncs Salesforce data on a 15-minute schedule. Its CRM data batch is fine. Storage: Raw events from Kafka land in S3 in Parquet format, partitioned by date and event type. This is our immutable raw layer, the source of truth we can always replay from. Cleaned and modeled data lives in Snowflake. That's where the analytics team queries. An iceberg lakehouse layer gives the ML team raw access through Spark. Processing: dbt transforms raw Postgres and Salesforce data into clean staging models, then into MART models. Star schema, fact orders, dim customers with SCD type 2, dim products, dim dates. A separate Flink job processes the real-time Kafka clickstream, joining clicks with orders in a 5-minute window to calculate real-time conversion rates, and feeding the fraud detection model. Orchestration: Airflow schedules all dbt runs hourly, handles dependencies between extract, stage, and mart layers, retries with exponential backoff, SLA misalerts to Slack. A daily compaction job runs on the S3 raw layer to merge small files. Serving: Tableau connects to Snowflake Marts for the analytics team. A feature store serves the ML team with point-in-time correct features for training and real-time features for inference. A lightweight REST API exposes real-time conversion metrics to the product dashboard. Observability: Monte Carlo monitors data quality, freshness, volume anomalies, schema changes. Great Expectations runs data quality checks as an Airflow task before any MART model publishes. PagerDuty for critical pipeline alerts. dbt's lineage graph is the map when something goes wrong. Here's the thing about system design interviews: there's no perfect answer. Every choice is a trade-off, and the interviewer knows that. Kafka over Kinesis, you get more flexibility, better replay semantics, a massive ecosystem of connectors, but you're on the hook for operational maintenance, zookeeper management, broker tuning, partition rebalancing. Kinesis is simpler but less powerful. Snowflake over Redshift, better separation of compute and storage, easier scaling, better concurrency handling, but higher cost at large volumes and less control over the underlying infrastructure. Flink over Spark streaming, true event at a time processing with millisecond latency, but a steeper learning curve, a smaller talent pool, and more operational complexity. If you don't genuinely need sub-second latency, Spark Streaming's microbatch model is easier to hire for and operate. dbt versus custom Spark pipelines. dbt is faster to develop, easier to test, and SQL native, but you're limited to what the warehouse can do. If you need complex Python transformations, custom ML feature engineering, or processing that doesn't fit into SQL, you need Spark. Many teams use both, dbt for the warehouse layer, Spark for the heavy lifting. The candidates who impress interviewers aren't the ones who name the right tools. They're the ones who name the trade-offs proactively, who say, I'd use Kafka here and the risk I'm accepting is operational complexity. Here's how I'd mitigate it with Confluent Cloud or a dedicated platform team. Who say, I'd choose Snowflake for the warehouse, but I want to flag that our cost model depends on how many credits the analytics team burns. Here's how I'd implement query budgets and warehouse auto suspend to manage that. Who say, I'm going with batch processing for most of this pipeline, and the trade-off I'm accepting is data freshness. The business question is whether hourly freshness is good enough. And based on the requirements we discussed, it is. That's the senior data engineer mindset. Not, I know the answer, but I understand the trade-offs and I can make a justified choice and I can articulate the risks I'm accepting and how I'd mitigate them. That's what this entire course has been building toward. Quick before we wrap up, you just sat through 90 minutes of system design fundamentals. That tells me you are serious. So let me be real with you. Everything we covered today, Kafka, Flink, star schema, idempotency, all of it, I go way deeper on it in this product. I'm talking full system design interview walkthroughs, step by step, the exact frameworks I would use if I were sitting in that interview room tomorrow. Edge cases, capacity estimation, the stuff interviewers actually grade you on. This video gives you the foundation. The product gives you the confidence to walk into an interview and know you belong there. Seriously, if you're preparing for interviews right now, this is something you should check out. The link is in the description. Alright, let's finish this. 90 minutes ago, you had a blank whiteboard. Now, you have a complete mental model of data engineering system design. Let's run through what you covered. Module 1, ingestion, batch versus streaming, and how to decide based on the business cost of stale data, push versus pull, and where CDC fits in, Kafka partitions, consumer groups, offsets, and replay, and why it's a buffer with memory, not just a pipe, pitfalls, back pressure, late arriving data, and schema evolution. Module 2, storage, data lakes for cheap raw storage, warehouses for fast analytical queries, lakehouses, Delta Lake, and Iceberg for the best of both, columnar formats like Parquet and why they make analytical queries dramatically faster, partitioning as the single biggest lever on query performance, and the small files trap, compute storage separation, and why it changes the cost equation. Module 3, processing at scale, Spark's lazy evaluation and DAG optimization, the shuffle penalty, and how to minimize it. Flink for true event at a time streaming, Lambda versus Kappa, and why the industry moved towards single pipeline architectures, data skew, how to spot it, how to fix it with salting and broadcast joins. Module 4, orchestration, airflow DAGs, and dependency management, idempotency as a first-class design concern. Every pipeline rerunnable by default, exponential backoff, service level agreements monitoring, circuit breakers, dead letter queues, data lineage, knowing the blast radius before stakeholders call you. Module 5, data modeling, star schemas, fact tables for events, dimensions for context, SCD type 2 for preserving history, the normalize in staging, denormalize in march pattern, grain decisions, and why modeling at the right level of detail matters. Module 6, the interview framework, radio, requirements, architecture, data model, infrastructure, observability, capacity estimation with back of envelope math, and the senior mindset, naming trade-offs proactively, not just picking tools. Every single concept in this course ran through the same e-commerce platform, 10 million events per day, hundreds of thousands of daily transactions, real numbers, real decisions. That's intentional. System design isn't a list of tools to memorize, it's a set of trade-offs to justify. Kafka over Kinesis because you need replay and multi-consumer independence. Lakehouse over warehouse alone because your ML team needs raw access alongside your analysts. Kappa over Lambda because maintaining two code bases is a tax you pay every sprint. DBT for the SQL layer, Spark for the heavy processing, because one tool doesn't fit everything. The justification is the skill. The tool is just the outcome. 3 concrete next steps. First, practice the radio framework on paper before you need it in a room. Pick a system you know, a ride-sharing app. How would you design the data platform? A social media feed. How do you handle billions of events from likes, comments, shares, and recommendations? A payment processor. How do you ensure every transaction is captured, reconciled, and queryable? Spend 45 minutes going through requirements, architecture, data model, infrastructure, observability. Don't look anything up. See where you get stuck. That's exactly what to review. Do it 3 or 4 times with different systems, and the framework becomes second nature. Second, build something real. Spin up Airflow and DBT locally, even with toy data. Pull a public dataset from Kaggle, e-commerce transactions, write data, whatever interests you. Build the full pipeline, ingest from a CSV, stage it, transform it, model it, schedule it with Airflow. Break something on purpose and fix it. The gap between understanding a DAG diagram and debugging a failed task at 2 a.m. is experience. The sooner you close it, the better. Employers can tell the difference between someone who's read about Airflow and someone who's actually wrangled with DAG dependencies, XCOMs, and retry logic. Third, use this course as interview prep. Before any data engineering interview, rewatch the module most relevant to the role. Storage heavy company, data lake or warehouse vendor, module 2 and 5. Real-time product, gaming, fintech, adtech, module 1 and 3. Platform team focused on reliability and developer experience, module 4. Generalist role, module 6. The framework covers everything at the right altitude. Here's the thing that separates strong candidates from great ones. It's not knowing the right answer. It's being the person in the room who says, I'd go with the Lakehouse here because the ML team needs raw access alongside the analysts. But I want to flag that this means we take on schema evolution risk and need to invest in data contracts. Here's how I'd handle it. That's it. Deliberate choices over defaults, name trade-offs over assumed ones, proactive risk flagging over crossing your fingers. That's senior data engineering thinking, and it's a skill you can practice, not a credential you wait to earn. You have the framework now, go use it. Thanks for making it through the full course. If this was useful, share it with a colleague who's preparing for interviews or building their first production pipeline. And don't forget to follow me on LinkedIn, where I talk extensively on data engineering focused on interviews. This is exactly the content I wish had existed when I was starting out. If you have questions, drop them in the comments. I read everything. Good luck. You're more ready than you think.